you can go out there and just check some of the problems out. Some of them look like this. It says factor that. How would you go about, when you look at that, how would you know to factor that and what to do with it immediately?
Well, you know they're both perfect squares.
Is what?
Perfect square.
It's the what?
The difference.
It's the difference of what?
2 squares.
2 squares. It is, do you all recognize that that's the difference between 2 squares?
Yes.
That this would actually be what? This is the same thing. Like that? Everybody okay with that? Everybody see how quickly I wrote it as the difference between 2 squares? Can you factor the difference between 2 squares? And the answer is yes, because it's going to be what? Just like that. Just that simple. One of them plus what the other one, one of them minus the other one. Okay, let me go back and ask you a review question, okay? Why is it that they ask you to factor in the first place?
Punishment.
For punishment, right? Generally
They
for
didn't feel like
punishment.
doing it.
Most students really think that though, really.
Right.
If you assign them enough factoring problems, they actually begin to think it's what? It's for punishment. It is really not. Because truly, what are they trying to do? What are they trying to do when they are asking you to factor a problem?
Irritate you?
We're trying to find what x and y equals. Trying to find what x and y equals.
Not necessarily.
See, we can do basic algebra.
Find the lowest form.
Find the simplest form of the.
Why? Why are they wanting you to find the simplest form? That's my question, is why?
Because they give you the non-simplest form.
The problems
Because-
cannot be solved without further information.
Look, the reason why they ask you to factor a problem of any sort is they are trying to desperately find, where in the heck does the graph of this thing cross the x-axis? The x-axis. Now, if you have a problem like this, and you got a graph like this, and if you happen to know that, let's just say, for example, that this is a 5th power equation, okay? 5th power equation. It could be any 5th power equation. And you also know that the coefficient in front of the leading term is positive. Who can tell me right off the bat what this problem looks like on the graph?
It's on the intercept 5 times. It's on the intercept, either the x or y axis 5 times.
Well, no. We don't know, do we? We don't know. Somebody, what else can you tell me about this? Somebody tell me, what do you know about this problem if that's what you see, and somebody says, there's the picture of a graph, what can you tell me about it?
That it's going to eventually cross the x and y axis.
Who can?
Or the x to the 5th, or the
remembers if you've taken a class here, what can you say when you're looking at an equation and you look at the exponents and you also look at the leading coefficient? What can you tell me about something called the endpoint behavior of any polynomial equation, which that's a polynomial equation? What can you tell me about the endpoint behavior? This is something you better know. You should already know it.
The direction.
This is 11:13. This is not 11:11.
The direction that the line's
Go
gonna
left
go.
or down?
Now,
If it's negative, it's gonna go down and to the right, or it's gonna be shaped like that, you know, on forever. And other stuff.
Where it's gonna rise and where it's gonna run.
Okay, look, y'all stop a second. Stop a second. Hell, this is time for you to know this, and don't you ever forget it. I know I've said this because to some of you, you've taken my class before, and you forgot. I want you to just take out a sheet of paper right now. I want you to take a sheet of paper out. You take a sheet of paper out, and I want you to put a big star, put that up. Put that up. You take out a sheet of paper, you put a star across the top of it, and David right important across the top of it. Okay? Then up under it, you can say endpoint behavior. Because you're going to need this piece of paper. I want you to do this with the piece of paper. You see what I've got drawn there? On the whole piece of paper, you need to make a great big huge box. And in this one, you put an X and Y axis, X and Y axis. There's going to be 4 of them. If there's 4 possibilities, folks, that's all. No more than 4 possibilities. And here's the first one. I'm going to just write an example down where you'll know this is what follows, okay? X squared, okay? This is an even exponent, positive coefficient, okay? And this is true for all even exponents and positive coefficients. Up on the left, up on the right. Up on the left, up on the right. Even exponent, negative coefficient. Down on the left, down on the right. And that follows suit for all of them of that nature. This one is x to the 3rd power. This is odd coefficient, odd exponent, rather. Positive coefficient. It is down on the left, up on the right. This one is minus x to the 3rd, odd exponent, negative coefficient, up on the left, down on the right. Do you see that? Now, all polynomial equations will follow that example. All of them will follow that example. I'll give you a second or two to finish writing them all out. Give you a second or two to finish writing them all out.
Yeah.
Everybody got it written out? I'll wait a couple seconds here to make sure everybody gets it all written down. Okay, is everybody ready? Everybody got it all? Now that piece of paper should stay with you, and you probably need to laminate it. Because from time before that you taken my class before, you should have remembered that. That is too important to forget. So don't ever forget that. Because you need to know just the snap of a finger by looking at a polynomial equation exactly what its behavior looks like. Okay? Now, let's go back to this one. Look at the one on the board. I don't care what it looks like, we know it's what? It's the fifth power. We can now say about that problem, there are 5 numbers in this world that will make that equal to 0. There are 5 numbers that will make it equal to 0. Now if you're lucky, if you're extremely lucky, and you've been given an ideal 5th power equation, then maybe, just maybe if you're lucky, that all 5 numbers may be what? Good grief, can you imagine all 5 of them being integers? What a wonderful example to give you. But you're probably not that lucky sometimes, okay? But we do know that there are 5 numbers that make it equal to 0. Okay? Now here are the possibilities. We know for a fact that one of the numbers has to be a real number. One of the numbers has to be a real number. The other 2 could be what? Imaginary. Because imaginary values come in pairs. So that's another possibility. The other possibility is what? 3 of them could be real numbers and 1, what? A pair of imaginaries. Am I making any sense to you? We also know what? We know that the problem is not going to turn any more than what? 4 times. It can. I didn't say it was going to turn 4 times. I said it cannot turn any more than what? 4 times. Okay? We also know that what? That its endpoint behavior is where? Down on the left, up on the right. Clear enough? So it's quite obvious, if you were able to take this darned equation and factor the fool thing, and you found that all 5 of its answers happen to be integers. Let's suppose that one of them was a -8, -5, -1, there's a 2, and a 6. Let's suppose we were lucky enough to be given an equation of 5th power, and we factored it in such a way that we can visually inspect it and say, wow, these are the 5 solutions. You can now easily do what? You can easily sketch this thing because you know it does what? That's what it looks like. It's a graph. So you know, if somebody gives you one and say, here's a graph of this thing, you say, well, maybe I don't know whether that's right or not. How would you know it would be incorrect if you had one of the endpoints going where? Up on this side and one of the other ones going up on the other side? Or what if you had both endpoints going down? Or what if you had one going over here and one going down here? You know that's wrong simply because that's what? That's positive, that's odd. Am I making sense? Somewhat. So that's what, yes.
Hey, if that was y to the 5th, then would it be across the y-axis?
If it was what?
Y to the 5th. Would it be across, would you have?
No, well, what they do is they normally put it what? They put the x-axis first and the y is always the vertical axis. So you won't have, I mean, you wouldn't even have it wouldn't be a polynomial if it was y to the 5th. It would be some other type of possibly hyperbolic equation rather than what? A polynomial. A polynomial would be what? Y is equal to x to the 5th, so forth and so on. This I'm going to erase away. You have this copy down, I hope. And so, let's suppose that you have this particular problem, okay? And you were able to factor this problem. And this is how it was factored. Fifth power, right? Fifth power equation? Everybody agree? Endpoint behavior? Endpoint behavior? Somebody?
Down to the left, up to the right. Down to the left, up to the right.
Everybody hear what he said? Like this, right? So we know it's down over here, up over there. Now we have to do what? Now we have to figure out the solution sets. Okay? What's the solution of that? -6.
-2. +3. +9. +2. You can't do that twice. +3.
Everybody see that? Did you see what he said? Anybody not see what he said? How many solutions are there? 5. Count them. Did you count 5? Now I want you to plot that graph. Plot the graph. Plot the graph. Plot the graph. Plot the graph. It would sketch the graph, in other words. What's that? What is that? What value is that? Sketch it. What is that? I don't know. Well, you just made a line go where you wanted to go, right? Just hurry. What the hell? Quickly.
Wait, if you wanted to do loop it back? Loop it back?
I don't know. Maybe.
Only one.
Maybe it does this.
Now one person got it right.
I got it
Oh, what
right
is right here?
Check that out.
What happened there? That's the solution, don't you forget that. Well, hurry up. Yeah, look at you. Hurry. Okay, so what in the world is this right over here?
He's writing on the
What did you crossed that line twice right there?
You know that's right.
Two people got it
Well, I
right.
didn't say no, you know that's right.
Oh, what
I
happened?
appreciate it.
I don't know.
I don't know.
Check mine.
Does everybody see what happens?
Check mine.
Yeah,
If it's twice, if it does it twice, then it's bounced.
Where's yours?
Right there. Wrong. Hurt.
Hurt.
It was right.
Hurt, Merc, put 'em in the.
I was right.
Ow! No, whoa, no, Lord. Oh, Lord, no. Do you see the problem, everybody?
Yeah.
Look at this. Both of you started up here like this. And then hell, you got here, you realize, wait a minute, if I go back through here, you know what some of you did? Hell, just turned and went back up through here. You know what the hell, I just busted back up through there. You don't have a bridge there, folks. You can't go just cross it at any place you want to. So we run into a problem, right? So what do we do to resolve it? We have to go back and say, listen to me. This is super, super important. This solution set right there. That's called a solution set of odd or even multiplicity. Okay? Now the minus 6 is the solution set of odd multiplicity because there's only one of them. The solution set of a minus 2 is odd multiplicity because there's just one of them. The 3 is an even multiplicity solution because they're what?
2.
And 2 is an even number. Even multiplicity solutions. Listen to me. When you have an even multiplicity solution, your line will not cross the x-axis at that point. Only 2 people got it right back here and here. And that means what? That you had to do something here to do what? To fix the problem, because here's the even solution, the even multiplicity solution. And that's what he does when there's an even multiplicity solution. How many of you realize that? 2 of you know. Wonder why? Mr. Jackson, I can tell you why, right? Oh, yeah. You took my class and I beat that hell out of you. Say, you know, you didn't do this right. I made you do it over and over and over again. But it's super important that you know to do that. Holly, did you get it right? I think you got it right. To 3 people, okay. Wow. Y'all are going to miss it, are you again? That's super important. If you have an even multiplicity, it means 2, 4, 6, 8, or whatever solution set, it does. Think about this, everybody. How many solutions are there to that problem?
2.
2. What are they? What are they? What are they? You better name them, hurry. I ain't giving you no more time. You're out of time. What's the solution set? 2 of them. Name them.
X and Y.
X and Y.
Gee whiz, folks. Factor the damn thing. Do you see that? What's going to make that 0? Somebody tell me what do you have to put there for X to make that 0?
1 and negative
A
1.
0. And a what?
Oh,
A 0. So what do you think the thing looks like? If you grab this thing, guess what it looks like? Guess why it only touches the x-axis at 0? Because it's even multiplicity solution. Do you see why? You can always, always, always factor the difference between 2 squares. Do you recognize that? Why? Why can you not factor the sum of 2 squares? Somebody tell me why you cannot factor the sum of 2 squares.
Because it's positive.
Somebody tell me why can you not factor the sum of 2 squares? You don't need to look looking back. There you go. Your answer's not going to be back there.
Because it's positive.
It's what?
Because you have to get positive and a negative.
Because it doesn't touch the x-axis.
What?
It doesn't touch the x-axis.
The fool thing does this, folks. It doesn't even come close to the x-axis, much less cross it or even touch it. You cannot find any real numbers anywhere that will make this equation equal to 0. The two solutions of the sum of two squares happen to be what? A what?
Two positive.
Imaginary solutions. You know, not the positive numbers. It's imaginary solution. Plus or minus what? Imaginary values. How can you possibly, look at this everybody, how can you possibly even begin to think that x squared equals minus 9? X is equal to plus or minus what? Somebody tell me the answer there.
Plus 3i.
It's what?
Plus or minus 3i.
It is plus or minus 3i. And 3i is what? Imaginary number. X is equal to plus or minus 3i. Do you see what it looks like? Do you see the solutions? Do you see the solutions? No, you do not. No, you do not. You don't see the solution up there. Show me up there where 3i's at. Plus or minus 3i. Not on there, is it? Because they're what? Those imaginary complex numbers are on what? In their own world. They're not in that world. Does that make sense? So the reason you can't see them is because it's not because they're imaginary. Folks, let me tell you something. They chose a poor name for that solution, imaginary. They didn't really mean to. It just happened. Because when you say imaginary, what does most people think? Does it exist? Listen, those numbers exist. And they are absolutely wonderful numbers. And have applications beyond your imagination. Because how do you think they solve AC electricity problems? With complex numbers. Complex arithmetic. So yes, and guess what? In electricity, they don't call it I for imaginary, do they? You know what they call it? J. J. No! It's not Joule. No, it's not. It's J for J factor. Just J. J, not a Joule. Man, who taught you science? What is a, okay, my turn. What is a Joule?
Where you measure temperature?
Which Joule are you talking about?
What?
Which Joule are you talking about?
Joule. Joule.
It's a measurement used to measure heat. Joules is heat, right?
Energy.
It's electrons jumping off.
It's what?
It's electrons.
Electrons not liking each other, jumping over here, jumping over here. All right.
I don't think so. It was a measurement. I'll show you, Mr. Schmuck, hands Google knows.
All right.
What? That's what you do when you have unlimited data. Burn. It's not talking to you. I wasn't trying to speak.
Okay. You might well take a time out. Because the timeout's going to be something we need to talk about. Not for this class, but for what?
Life.
For life. Yeah, very good. For life. I mean, I do not want you to leave this school and not know this. Okay? Truly. That's it. Would sort of be an embarrassment. And And the reason I make a big deal out of it is because I hear this all the time, out and about. And you can't just go up to somebody and say, no, what you're saying is not correct. And I don't do that. I just have to sort of shrug my shoulders and go, oh. But now you can write this down if you like, and some of you may have already done this. And some of you have taken my class before. You may already have this in your notes somewhere. Let me see if I can get a better marker.
Are you noticing? Are you?
Okay.
Mass is gonna be grams. Distance.
This is
gonna-
something you need to know, folks. Don't you leave the school without knowing this. What is the unit of weight in the English system?
Pounds, says the weed.
What is the unit of weight in the metric system?
It's like,
No, we just learned this in biology.
What is the unit of weight in the metric system?
Kilo like a decade unit, this is 70 milli. I don't know.
Yeah.
Liters, it's liters.
No.
No, that's measured.
Oh my God.
Grams.
Somebody please help her.
Grams is mass. I knew that. Let's just fill out the ones we do know.
Let me tell you this. Don't you forget this. But the measure of the mass of an object in the metric system is a kilogram.
I knew that.
Don't you ever dare say that something weighs so many kilograms. Because Hollywood has already messed you up enough. What did you catch him with coming across the border? Caught him with 5 kilos. What the hell's 5 kilos of gasoline? You caught him with 5 kiloliters of gasoline? 5 kilos. Kilos is a prefix, not a measure of anything. 5 kilos. Yeah. Smart aleck. They will strangle them when they do that. How much does it weigh? Well, it weighs about 30 kilograms. Don't you ever say that something weighs that many kilograms. The weight in the metric system is a what? Is a Newton. Is a Newton.
Yeah, so
You act like you never heard of a Newton before, folks.
Gotta be
That's like that. Yeah, hell, I know Sir Isaac and Fig, and that's about all I know. But now you know what? That the measure of weight in the metric system is newtons. And don't you use anything else. In Germany, they go to the store and they buy the meat at the market in what? In mass. So many kilograms. They buy it by mass. If you went to the store in America and you bought it in the same units, like mass, you'd have to go get what?
Pounds.
Hell, I've already written pounds here. That's weight. It is what?
slug.
A slug.
A slug.
People say, what the hell?
Yeah, that's what I was saying.
What the heck? You like you've never heard of a slug?
Like a bug.
Don't. Why you put salt on top of your beer to keep slugs out, right?
Sure. Well, I don't
No, yeah, that's not. No, really. I mean, what do you think the definition of a pound is? What is the definition of a pound? It is a slug foot per second squared. You look puzzled as you can be. I never seen such puzzled look on your faces. It's a slug foot per second squared. Force is your weight in pounds, right?
Right.
You're putting a weight on this earth. And it is so many pounds. How do you get a force? Force is equal what? Mass times what? Acceleration. Mass is in what? Slugs. Acceleration is in what? Feet per second per second. How do you get a Newton? It is the same way, mass times acceleration. Kilogram meters per second squared. Kilogram meters per second squared is a Newton. Don't you forget that. We measure distance in what is feet, and this is what?
Meters.
Meters. Work is defined in all systems as being what?
Hard.
Is force times distance, provided that the force and the distance is in the same direction. That the force and the distance is in the same direction. Don't you understand that? How many of you can do this? Can you add 3 pounds and 4 feet together?
No,
Why not?
because they don't have the same.
They're unlike terms. Unlike terms. Period. Can you multiply unlike terms? Can you multiply unlike terms?
Yes,
No.
yes, yes.
How are you going to get out the door?
No.
You can't get out the door unless you know how to multiply unlike terms. How do you get out this door? You can't get out this door until you do what with this handle?
Twist it.
Put force on it.
You
Have a
put
gentleman
something
open it.
called torque. I'm torquing this by what? Force
In a certain direction.
times the moment arm. Force times distance. The door opens by me doing what?
Push.
Pushing
Force.
on it. Once I do this, then look. I am torquing this door. I'm putting so many foot-pounds of torque on this door. So yes, the measure of work is foot-pounds. When you go get your wheels put on your car, they torque them by what? Foot-pounds. They do work, and it's what?
Which is called labor.
In the metric system, they do the same thing on this what?
No, joules.
A Newton meter. A Newton meter is work. And if you do 1 Newton meter of work, you have produced 1 Joule.
Joule.
That's right. That's where it comes from. You got time in here, and everything is in what?
Second.
Seconds and in both units. So if you do 1 Newton meter of work, or 1 Joule of work in 1 second, you have produced
1 watt.
1 watt.
1 watt of power. 1 watt of power. If you ever get the opportunity, I would like for you all to try. I'll see if I can't locate it again somewhere. This device I used to have in the physics lab that would allow you to turn a crank. And what you're doing is you're generating power by turning this crank. And it's very easy to turn as long as you're just going slow. But you're not producing very much power and work. But it's when you start to do what? You start to get it faster and faster and faster. It's when it starts to oppose you more and more and more. It's called the Lenz's law effect. It's operating against you. So all of a sudden you find yourself twisting it until you get a little tiny flashlight of 1 milliwatt to light up. About the time you feel like your arm's about to fall off, you have lit the light bulb. And you realize how much work it took you to do to make that little milliwatt of power. And then you go back and you realize you only pay so many pennies for a kilowatt hour. a million times that much for a whole hour. You'll never complain about your light bill again. Trust me, you won't do it. Once you sit there and you make that thing get a milliwatt of power, and your arm's about to fall off, and then you'll say, wow, I can't imagine producing a million times this much for a whole hour for about 12 cents. Or maybe less. Our system. How do we measure power in our system? The English system. That's the one you're familiar with. That's the one you grew up with. Right? How do you measure power in the English system?
Resistance over velocity, voltage.
How do you measure power? Yes, you do.
Georgia power measures the power.
What?
Georgia power measures it.
How do you measure power?
On your light bill.
Voltage.
The meter in your house?
I can't believe it. Especially you guys. Now, you girls I'll sort of forgive. But hell, it's horsepower.
Oh.
What do you mean, oh? Horsepower. How do you measure horsepower?
In your Mustang.
If you 550 foot-pounds per second is 1 what?
Horsepower.
1 horsepower. How did they get that?
Had a horse walk around in a circle and did some kind of.
Got a horse pulling a carriage.
Is that an ass?
They tied a rope around the horse's neck and put it over a pulley. And they realized he could do what? He could pick up 550 pounds of weight off the floor in 1 second continuously. Do that for a continuous period of time. That is the insane way that we measure power in our system. I'm not making this up. It's too crazy to make up. I mean, the same thing. Inches, a foot. Duh. Where did that come from? How do you know 12 inches is equal a foot? Who made up a foot? Who made up the titanium bar that's in Washington under heat and humidity control conditions that says that this is our unit of measure? And this is what our base unit is right there. I think they did what? They measured a king's toenails. So many of them, 12 of them made a what? They said a foot. That's what they said. So that's what they said. And so they made it a foot. 12 of those toenails. No rhyme, no reason. What is the base unit of measuring a meter? And there's so many wavelengths of krypton gas, it doesn't need humidity control and temperature control conditions to remain the same always, always, always. It's the most sensible system in the world. I want you to picture yourself building a little tiny box that's 1 inch by 1 inch by 1 inch. And we know without a questionable doubt that we have 1 cubic inch of water. Well, the volume is 1 cubic inch. Right or wrong, right?
Right.
Now the question is, how many ounces of water will go in there? And don't look at me for the answer because I don't know, don't care. I really don't care. Because I don't want to go through the problems of doing what? Trying to figure it out. I want you to go back now and picture yourself building yourself a little tiny box that's 1 centimeter by 1 centimeter by 1 centimeter. We know for a fact that the volume is 1 cubic centimeter, 1 cubic centimeter. That box will hold exactly 1 milliliter of water. And the mass of that 1 milliliter of water is 1 gram. And you raise that 1 gram of water 1 degree Celsius, it costs you 1 calorie of heat. Now for homework, I want you to go home and tell me, take that cubic inch of water and tell me how many BTUs it's going to take to raise it from 1 degree Fahrenheit. No, just forget that.
Thank you.
Just forget that.
And I was like, no. she'll call me
You
for
should
tomorrow.
say what I say. Who cares? That's a sensible system. That's the system that's sensible. I would think, good grief. I have an ounce of something behind my back. Gee whiz, I ain't telling you.
I hope it's my favorite.
You don't have a clue what it might be. It may be an ounce of Pepsi. Or it may be an ounce of sugar. Right? Could be. So what's wrong with that picture? We're using the same word for 2 entirely different things. Now I go back and I say I have a milliliter of something behind my back.
It must
You
be
know
liquid.
it's liquid. I've got a gram of something behind my back. You know it has to be what? Dry measure. There's no question about it. Our system of measure is crazy. Makes no sense. Only one president tried to get it all changed.
Carter. Jimmy Carter.
Exactly.
You didn't think you were going to know that.
You remember? Thank you. You remember.
That's my favorite president.
Some of you may not be old enough to remember. Y'all know Jimmy Carter?
No.
Y'all know about Jimmy Carter?
You probably weren't born yet when
Huh?
he was president. You probably weren't born yet when he was president.
Well, I know, but you know who I'm talking
I
about.
know you are, who you're talking about.
What did he do?
The first president from Georgia.
Yeah, but what did he do? What was his background?
Is it the peanut guy?
He had a peanut farmer. Gee whiz, come on. You see what happens when you let the people from other states tell you who you have as a president?
He's an author.
He was what?
An author.
Of course he is now, but what is his background?
He lived on a little prairie.
He's a
He's a
nuclear physicist.
He's a nuclear physicist.
Nuclear physicist.
Submarine.
The hell, everybody claims he's a peanut farmer.
But he did that too.
That's how bad they misled you. They had you believing he was a peanut farmer. How many of you thought he was a peanut farmer? Look and raise your hands up. Yeah.
I went to the peanut farm, so I know about the peanut farmer. Hey,
I still have the cartoon that was placed in the New York Times when he was sworn in as president the next day. The next day's cartoon. And guess what it was?
a peanut.
It was a picture. They had drawn and sketched a picture of the White House. You know how the oval driveway is? Well, the picture showed white wall tires planted halfway in the ground, all the way around the driveway, and 2 porch swings hanging on the front porch, and one of them was broken, and some hound dogs laying up under one of them. And in the backyard at the White House, they had a Plymouth and a Chrysler up on cement blocks. Now that's what he was. That's how they portrayed him to be, a somewhat stupid country hick from the state of Georgia, when he's a nuclear physicist. Probably one of the smartest, I don't care whether you like him or not, he's probably one of the smartest ones we've ever had an officer during my lifetime anyway. One of the smartest ones. He may have not have governed, well, I don't care, it doesn't matter to me, I'm just looking at his credentials.
Washington was the big one.
No, he put solar panels on the White House and Reagan ripped them down.
That's right, put solar panels on the White House and Reagan ripped them down.
Actually, George Washington was from Britain.
He also, guess what else he did? He took away the 10-year period of time that we'd go and be in the metric system. He said, no, if they want to learn, they're going to learn our way. You know what? We're still struggling to catch up, folks. We're still struggling to catch up.
Reagan's background, he was an actor, right?
Yep. England, look what happened to England. England used to be the what? The sun never set on the English Empire. Is England a very strong country now? Not really. Why not? Because they refused to take part in the Industrial Revolution. No, let everybody do as we do. No, hey, we. So guess what? They fell behind. So if not careful, we have to be careful that we don't fall behind. And maybe someday that they'll start this back and say, look, let's see if we can't get back on the same system with the rest of the world. To do it now, you ever try to work on a car?
I don't think I want to start all over though.
9/16 wrench is too small. What are you going to get?
What?
Yeah, 9/16 is too small. What wrench are you going to pick up next?
5/8.
You don't know.
The one
If a 12 millimeter is too small, what you going to pick up?
11.
13.
That's too big. Another.
Yeah, you'll get it right in a second.
On the thing. I have sand in my pockets.
Hell, you just use a pair of channel locks.
Yeah. Bye, Chris.
If you happen to know what those are, by the way.
Yes, on your phone.
I was with a friend, and she was saying, look, I got to get my battery, and they appear to, could you come up and help? They're Walmart. God, gee, please don't let me have to go up there. What I do, I put my tools in my car. And my friend said, what the hell are you doing that for? Okay, we got to go up there and check on this battery. We go up there. They were still struggling trying to get the battery out of the car. Waiting. I said, wait, hold a second. Walk out there and I said, look, why don't you go get me a pair of channel lock pliers? I'll show you how to get this battery out. Guess what he brought back? A dang crescent wrench. I walked over to my trunk and I popped my trunk and I picked up my tools and I had a big pair of channel locks. I said, that's a pair of channel locks. I said, that's a crescent wrench. He said, we don't have any of those. I said, you got a store full of them, man. They got a bunch of them in the store. Go in there and get you one. If you don't have one, go get one and put it back there and get out of the way. I'll take this battery. I took my own battery out, went in the store, got my own battery, walked right out the door with it, put it in the car. They'd already messed up the cable. Had to put a new cable on. And now the guy said, now, Jim, I know why. You put your tools in the car. Said, you know what? Y'all ought to give him a discount or her a discount because he had to put a battery in for it. Well, I can't. I'm not authorized to do that, but I can call the manager and let you talk to the manager. Why do you think I want to talk to the manager? Because the manager's the guy that hired those idiots. What good is he going to do me talking to the manager? Anyway, I'll give up. That's all. No, I'm not quit talking. I'm not taking this. Oh no, I'm just quit talking. But anyway, folks, this is important, really. Don't forget this. Did y'all already know this?
Yep.
You're going to help a line same as stealing.
That was cute. Go to help the lion thing stealing. Rick's
I don't know how we managed to go from factoring
The metric system.
to the metric system, but we did.
To talking about your car.
What'd you do this weekend?
But really though, I hope that you do understand the significance of factoring. That it is not something that they ask you to do for punishment. It is something they ask you to do to help you do what?
Learn.
Sketch. Look, you've got to be able to sketch the equations. If it does like that, you know, just by looking at that, you know it's an odd power, right? Odd power. You know it has to be a third power or more, because why? There's three solutions, right? Has to be a third power. Doesn't turn any more than what? Twice. Now, but why do we need to know this? Because certain equations like this, for example, the fourth power equation, may be an equation that may be graphed a little bit different. It may look like this right here, something like this. Or you may have a third power equation and you really like to know at what points is the function increasing, okay? And as you can see here, that you can tell that the function is increasing because the slope is getting what?
Higher.
Steeper, 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 okay? And then over here the slope becomes negative. Over on this side is positive. That's a positive slope, that's a negative slope. So how can you possibly go from a negative slope to a positive slope? You must have to do what?
Peak.
Cross the zero. You have to have a slope of zero. You have to have what? You go from a decreasing slope or a negative slope, right, to suddenly a positive slope. So somewhere in between here and here, you have to be what? There has to be a slope of zero. And when it's the slope of zero, you have actually found the vertex, or the vertices if you got more than one. You have found the vertices of that equation. And that's the important point. And you know what they're called? Who knows what they're called?
Vertices?
They're called what? They're called critical points of first order. Critical points of first order. So what do you think that means? It means they're critical.
They're important.
Critical points of first order. Then I go back and I say, take a look at that graph that you see here. And if you can sort of picture this as being what? Look over this side over here. Does this sort of look like something that would hold water? Yes or no?
Yeah.
Of course. Now, take a look at some point over here. Does this look like it's going to hold water?
No.
No. So you actually go from what? Not holding water to holding water, right? Everybody see that? You see it goes from not holding water to holding water?
Convex and concave. Convex and concave.
That's right, yeah. We're concave or convex. So, but look, there's got to be some magical point along here, somewhere along in here, that occurs from not holding water to holding water. Am I making sense? There is a point on that line. If you're walking along this line, all of a sudden you're going to hit what they call a critical point of second order. Critical point of second order, where it goes from what? Concave down to concave up. And you step on it and stand there on that point. That's the what? Critical point of second order. I've screamed all I'm going to scream. Fussed all I'm going to fuss.
Amen.
I quit.
Amen.
I'll come back on Thursday. Get another dose of this.